Good morning or good evening, depending on the time of the day you're watching my presentation. My name is Tito Andriollo. I work at the Technical University of Denmark. And my presentation is about how to combine X-ray tomography, digital volume correlation, and finite element modeling to study the process structure property relations in ductile iron. The work that I will be presenting is the outcome of collaboration between the Technical University of Denmark, Magma, and Eindhoven University of Technology. First of all, why do we do research on this material? The reason is that ductile iron represents 25% of the casting production worldwide, and in key European industrial sectors like energy production and transport, there is a strong request at the moment to reduce the weight and improve the efficiency of large ductile iron components. The idea to achieve this objective is to improve the control over the mechanical properties, which is also part of the European strategic roadmap for low-carbon energy technologies. It's difficult to control the mechanical properties of this material. The main reason is the very complex microstructure. The simplest case we can have is the ferritic ductile iron, which is a composite made of graphite particles embedded in a ferrite matrix. And already in this case, there are a number of parameters that can affect the mechanical properties, like the particle size, shape, the ferrite grain size, and many others. And I want to stress the fact that this is the simplest case. We can have much more complex situations, like in perlitic or austempered ductile irons. So because of this complexity, the identification of process structure property relations which are reliable and also have general validity is a challenge. Fortunately, the recent developments in X-ray imaging techniques have created new possibilities to investigate ductile iron at the level of the microstructure. And I want to emphasize that this material is particularly suited for X-ray-based techniques because of the high absorption contrast between the graphite particles and the surrounding matrix. So as an example here, I want to present an analysis of the local 3D strain distribution that we have performed recently. What we did was to consider a small tensile specimen made of a standard ferritic grade of ductile iron. This specimen was tested in tension while imaging in situ with X-ray tomography. And then we quantified the deformation using digital volume correlation. Digital volume correlation is a technique that allows establishing a mapping between two images. The first image represents the material microstructure before deformation, and the second image represents the material state after mechanical deformation. So digital volume correlation provides you with a mapping in the form of a displacement function, and then from this displacement function, it's actually very easy to compute the strain. And this is a contour that shows the equivalent for mesostrain over the central cross-section of the tensile specimen, and clearly shows how heterogeneous the deformation pattern is. Having access to these advanced data is of course fantastic, but it would be even better if we found an explanation for what we see. And in a case like this one, it's actually not easy to tell whether the strain pattern is just a consequence of the inhomogeneous graphite distribution, or if other aspects come into play, like for instance, microsegregation or the presence of residual stresses. In this context, we believe that finite element modeling is actually a fantastic tool to combine with experimental data in order to gain mechanistic insight into what is going on. And in this particular case, we developed a three-dimensional finite element model of the central region of the tensile specimen. And this model has two very important features. The first one is that the real morphology of the graphite is accounted for based on X-ray tomography. And secondly, we use the displacement field reconstructed using digital volume correlation to apply the boundary conditions in the model. So in this way, we make sure that the model volume deforms in exactly the same way in which it was deforming during the tensile test.
So the main advantage of a model like this one is that the output can be compared to quantities measured at the macro scale, like the tensile force or the lateral contraction, but also at the micro scale, like the strain field. So meaning that we have the possibility to perform a multi-scale validation of the model. And in this case, we use this advantage to reveal the impact of local residual stresses on the way the material deforms during tensile testing. And I also want to add that this type of modeling provides advantages at the macro scale in terms of accuracy of the tensile force, the predicted tensile force and lateral contraction, compared to traditional models based on idealized microstructure. And what is interesting, in my opinion, is that 1/3 of the improvement in accuracy actually come from accounting for the real boundary conditions during tensile tests. And the combination of tomography, digital volume correlation, and modeling, finite element modeling, can also be exploited to estimate quantities which are either difficult to measure or difficult to estimate with modeling tools alone. And in the final part of my talk today, I want to show you an example of these, which relates to a long-standing problem ductile iron, which is how to explain the impact of the graphite size and distribution on the fatigue crack growth. It is commonly accepted that coarse graphite morphologies give rise to a crack path with a high tortuosity, and this means higher energy that is dissipated and eventually means that the crack slows down. So the point which is still not clear is actually which factors control the tortuosity of the crack. And in our study, we started by observing that the graphite nodules act as attractors, which is also the impression that you have by looking at this image here. And then we hypothesized, based on this observation, that the crack path is actually determined by the micromechanical stress field induced by the nodules, as well as by the manufacturing process. So to verify this hypothesis, we would need to, of course, measure the stress field in between the graphite particles. Unfortunately, this is not possible to do experimentally because of many reasons. So what we decided to do was to estimate the stress field in between the graphite particles in front of the crack using an experimental numerical procedure. Specifically, what we did was to consider a crack growth test, and we performed this test while imaging with X-ray tomography. And then we used digital volume correlation to reconstruct the shape of the crack. And I want to emphasize that this is not easy because in a standard X-ray tomogram, it's actually not possible to distinguish the particles from the main crack due to the fact that I have approximately the same level of the intensity. And then based on the real geometry of the crack, we developed a finite element model of the region of the material surrounding the crack tip. And in this model, as before, we account for the real morphology of the graphite, as well as for the real boundary condition taking place during testing. And we use this model to estimate the micromechanical fields in front of the crack. These fields were processed statistically, and eventually we found a very clear correlation between the crack propagation path measured experimentally and the maximum principal stress predicted in the matrix. So this is actually a strong argument to show that the crack propagation path is determined by the micromechanical field. So to summarize, the impact on the mechanical properties of the microstructural features in a material like ductile iron can be hard to investigate and to understand using advanced experimental methods alone. So in this situation, the combination of tomography, digital volume correlation, modeling can provide a solution. First of all, because it enables a multi-scale validation, and secondly, because it allows you to access quantities that are very difficult either to measure or to estimate using numerical tools alone. I didn't have much time to go into details in this presentation, but if you found my talk interesting, you're more than welcome to take a look at our ResearchGate project page, where you can download all the articles referenced in this presentation and also get a glimpse of our activities in the field.
Thank you very much for listening and enjoy MacWasp 15.